Annually, landmines kill an average of 10,000 people and maim around 20,000, with over 40% of these victims being children. As minefields block essential travel paths and render large areas of land unusable for agricultural and industrial developments, they directly impact the local economy and the well-being of the locals. The stages in traditional demining are laborious, dangerous and expensive. After marking off the area to be cleared and removing vegetation, detection technology is used to search for potential landmines that may be buried underground. Suspected areas require manual excavation by removing the soil around the object, until it can be confirmed to be a landmine or a false positive through visual identification. After this, if a landmine is present, it can be safely neutralized. The manual excavation stage poses the greatest threat to safety, and it accounts for 45.5% of accidents in the demining process, as the deminer is in constant close proximity to the landmine, which may be activated due to a minor lapse in judgment or deviation from operating procedures. This project considers how to automate this process, making it both safer and faster. The aims of this project are to investigate and design a prototype tele-operated robot capable of soil excavation around a landmine for humanitarian demining purposes. The weight of this prototype must be under 15 kilograms for portability, and the cost must be less than £1,500. The tele-operated robot system is split into 6 subsystems. Each of these subsystems make it possible to achieve the aims of this project. The Robotis Open Manipulator robotic arm was selected and adapted for use in this project. It has 4 degrees of freedom, a maximum load of 500 grams, and a maximum reach of 25.2 centimeters. This provides it with enough freedom of movement, torque, and reach to move an end effector in such a way as to dig soil to a depth of 15 centimeters, which is the typical maximum depth of an anti-personnel landmine. The arm was also simulated in order to test code on a virtual model for quicker and safer development. The arm was then adapted by adding newly designed end effectors to accomplish the task of excavating soil. A scoop and a rotating bladed barrel were designed and 3D printed to find the best method of using a robotic arm to dig as desired. The Raspberry Pi 4 acts as the central computing system for this excavator and has been set up as a Wi-Fi hotspot to allow devices to connect and access the robot wirelessly without an internet connection or router. This includes controlling the robotic arm and viewing camera streams. The camera subsystem enables the deminer to view the excavation site at a safe distance, thus facilitating teleoperation. 2 USB cameras were used for this, which provide flexibility for adjusting the view of the site. A simple power bank was used for the Raspberry Pi, whilst a LiPo battery was used for the robotic excavator. The use of these power supplies allows for this project to be a light and portable solution. The web app serves as the point of contact between the user and the robot. Combined with the cameras, the web app makes the teleoperation of the robot from a safe distance possible. The purpose-built chassis is constructed using 3mm acetal and contains 2 sections, a base plate which houses the components and a casing which protects them from contaminants. Separation of base plate and case allows for purpose-built cases to be designed if the environment of operation changes significantly. The roof has holes for mounting pegs and a large surface area for weights to be added ad hoc to give the robot stability during its operation. The chassis was constructed as per the design CAD models, and the components were arranged on the base plate, resulting in the successful construction of the robot. This robot was then tested by placing a surrogate landmine 15 centimeters deep inside a container filled with topsoil. With the barrel end effector in use, the soil was able to be dug up. However, the robot arm would fail to uncover the landmine before the servo motors in the arm would fail. In a real-world application, the robot would excavate soil to the side of the landmine instead of above it, as demonstrated. When the scoop end effector was in use, the soil was successfully dug up. This time, the surrogate landmine was able to be spotted by the camera feeds on the web app in a time of 39 seconds from the start of operation. And as the force exerted by the robot is less than the required weight to detonate an anti-personnel landmine, there is no risk of detonation. To further improve the method of tele-operated excavation, future work that can be done involves alternative designs to the robotic excavator, such that a more effective barrel end effector can be used for quicker excavation, integration and incorporation of image processing tools like blob detection to aid the visualization and detection of a landmine. The project was successfully able to satisfy the aims of producing a cheap and lightweight robot, which is able to excavate soil via teleoperated control. And that brings us to the end of this video. Thank you for watching.